So, now we are in segment 4 of module 4, in which we are going to analyze Valiant's routing, which we saw in the previous segment. So, let us we need to ask ourselves if that algorithm is any good, and let me quickly remind you of what the context is. So, we have a synchronous network on an n-dimensional hypercube. And each node I has a packet P I, and the packet P I must reach a destination node pi I, and pi is basically some arbitrary permutation, and you must minimize the number of rounds. So, that is the problem we have. And recall that there was a bad news for deterministic algorithms. Basically, there is a square root of n term that you cannot avoid. So, what we did was we randomized we came up with a randomized algorithm. Basically, our claim, which we haven't proved, but we hope to prove in today's segment, is that this randomized algorithm will complete permutation routing in O of n time, and that will succeed with high probability. Okay. And what is this? So, well, this randomized algorithm uses bit fixing as a sort of a subroutine. What is bit fixing? Basically, just fix it's a way to go for a packet to go from one node to another node by just fixing bits one by one from left to right. But what is important is that's not a randomized algorithm, it's a deterministic algorithm, so it's not good enough, which means that you need a slight modification. This randomized algorithm, where we go through two phases in which the packet goes from the starting node to a random destination using bit fixing, and then from that random destination to the final destination again using bit fixing. So, these two phases that we need, and this algorithm we claim has the nice property that it terminates in O of n rounds with high probability. Okay. So, now we are ready for the analysis. Some preliminary thoughts. So, one thing to start off with is clearly needs omega of n rounds. Why is that? Yeah, bit fixing is one specific thing, but you are on. So, the diameter of this network is n, lowercase n, which means and bit fixing gives you the intuition as to why the diameter is n, and because the diameter is n, there can be always permutations where a packet has to traverse n edges, and therefore, it will at least be omega of n rounds. Yes, that is the other thing. So, the random number is the destination, but even the source and the destination, the adversary can actually decide. Say for example, the adversary decides that the packet at 00000 has to go to destination 11111. Then all the n bits have to be flipped. So, let us look at it. I mean, one thing is there hope. When we want to prove O of n, we want to make sure that there is enough intuition to say that there is enough hope to even proceed forward. Okay. So, let us try to establish enough hope that there is that we have. So, there are a capital N number of packets, each of them will have to walk for at most O of n steps. Okay. So, that itself means that there are capital N over lowercase n number of hops that have to take place overall. Okay. And how many edges are there? Well, there are this many edges. So, n is lowercase n is the degree of each vertex, and there are capital N number of vertices. So, this many edges are there. So, if you look at the number of hops over the number of edges, that itself is, so this is sort of the good news, if you will, in the sense that there are sufficient number of edges for you to get the packets across. We do not know how, but at least if it were the case where we do not even have sufficient number of edges, we would be in bad shape. We have sufficient number of edges. So, there is hope, but the issue that we need to be aware of is that if let us say one or two packets get stuck somewhere and they cause a delay, and therefore, a lot of other packets come and get stuck there, and then there is this ripple where a lot more, and because of that delay a lot more packets get stuck and so on. This ripple effect is what we should be able to claim will not happen. Okay. So, let us get into the analysis. So, let us start off with some preliminaries. Okay. So, one thing we are going to do is we are only going to focus on the forward direction, okay. Phase 1 basically. In the back, sorry, not I would not say, I guess I should probably not use the word forward direction, phase 1. And phase 2, we are going to essentially hand wave in this segment, but it is an exercise for you to think about how whatever we discuss in class will apply to phase 2 as well, and complete the thought process needed to convince yourself that phase 2 also will work fine. Okay. So, we are going to focus on phase 1. Okay. And now in phase 1, let us focus on a particular packet P. Okay. This particular packet P is starting from SP and it is going to RP. Okay. And we have a picture for that. So, starting at SP and going to RP. And along the way, in each edge that it traverses, there is going to be a queue. So, it will have to, if the queue is not empty, it will have to get into the queue, wait for its turn to get out of the queue, and then traverse the edge. Okay. So, this is the context. This path that this packet P uses, we are going to denote that by uppercase P, and that can have at most n number of edges. Why? Well, because we are doing bit fixing, right. And another important property of this thing, if each of these edges are representing a bit that was fixed in sequence from left to right. So, some of the bits might be skipped. Why? Because the current address and the destination already matched, but you never have it where there is a bit in the right side that got fixed and then a bit in the left side. You will always be fixing from the left to right. Okay. All right, let us make a first attempt and let us see where it takes us. Okay. We want to bound TP, which is the time taken by P to traverse this packet P to traverse path P. Okay. So, now how, and whenever we have this large variable, we want to try and break it up into smaller pieces. So, how do we do that? We define something called XE. Remember, capital P is made up of a lot of edges. So, this E is one of those edges, and XE is 1 plus the time spent by P, packet P at the Q in edge E. Okay. Why the 1? 1 is the actual time it takes for that edge for the packet to go through that edge, but before it even went through the edge, it had to spend some time in the queue. That is taken care of by this part. Okay. And now you can see that uppercase TP is summation E over all the edges in that path XE. Okay. So, we have a way to take this TP and break it up into smaller pieces, and now hopefully we can use Chernoff bounds. Okay. What might be an issue with this? This is the problem here. So, these XEs, there are, well, let us talk about a minor issue that possibly could be addressed first. One is this is not a 0-1 variable, okay, but that can be addressed because we can go back to the Chernoff bounds technique and massage it to work for these types of small variables. But even if we did this, the XEs are not independent, and for Chernoff bound to work we need independence. Okay. So, that is the problem. Okay. They are not independent. So, this will not work. So, we have to refine the analysis somehow, and in particular we have to refine it so that we go after a certain quantity. We want to try and define a quantity that can be broken into small independent pieces, and then we can use Chernoff. Okay. So, let us try to see how that can happen. So, let us get back to our path P, okay, and let us try to see how that path P might interact with some other path P prime. Okay. So, now you have a packet lowercase p prime, it is making its way, and that it is through a path uppercase p prime. Okay. Now, here is an interesting property here. Let us say Well, one possibility is that they never converge, the set of edges they use are always disjoint. That is great, then that means there is no interaction. But if they were actually going to interact, there will be a vertex at which they come together, okay. They will converge at that point, and they may follow each other for a little while, and then at some point they will diverge. Let us say they diverge, will they ever reconverge? So, they will never reconverge, because the moment they diverge, that at that point they fixed different bits, and when they fix different bits, their left side of is always different, the prefix is different, which means that they are never going to be able to find a way to converge again. Okay. So, this is a good property to keep in mind. Okay. It will not come in right now, it will come in shortly, but easy to understand property. Okay. Let us now try to understand these interactions. Okay. So, now what we are going after, let me give you a sneak preview, we are going after H, which is the number of packets that interact with path P. So, this quantity we can try and break things down. Okay. How are we going to break this down? We are going to define this quantity H parameterized by P prime. Okay. And that is going to be 1 if this other packet P prime uses any edge used by P, basically at some point they converge, 0 otherwise. And if you think about it, H P prime and H P double primes, when P prime is not equal to P double prime, are independent. Why are these two quantities independent? H P prime is it is just another packet, P double prime is another packet. So, if you have two packets, H of one packet and H of the other packet are independent. Basically, either of them interact with path P or not. The permutation, what permutation did we choose in phase 1, or was it even a permutation, whatever it is, the destinations? It is random. So, for each packet, the destination was chosen independently at random, right. So, if you have a packet that is starting at something, that packet in that node tossed n coins, and that defined where the destination was. It had nothing to do with what some other random destination was chosen by another node. Okay. So, the paths chosen by P prime and P double prime are completely independent of each other, and therefore, whether they interact with this path P that we are interested in or not is completely independent for each other. This one is any edge used by P, and the reason is if it just uses a node, then there is no delay caused by it. Okay. So, now once we have established this independence, we can ensure that we can basically establish that this capital H is the summation of these individual HPs, HP primes rather. Yeah.
Can you repeat the independence argument? I didn't get it.
Okay. So, what we care about is a path P. Okay. So, this is SP to RP, this is our path P, and we are asking, okay, there is another this is the path P, capital P prime chosen by this guy, this lowercase p prime, okay. And then there is this other path P double prime chosen by P double prime, okay. Well, in this case I have drawn it like they are interacting with this path P that we care about, but whether they interact or not is independent of each other, because what are these two paths? So, let us take this path P double prime, it was this packet P double prime. So, it is basically source of packet P double prime all the way to the random destination of P double prime, okay. And the source is fixed, but the random destination was chosen completely uniformly at random. So, now the question is, there is a certain probability with which this path will interact with this path P double prime will interact with P, okay. But our claim is, what is our claim? It is independent of whether P prime will interact with P or not, okay. We are not claiming that the probabilities of interactions are equal or unequal or anything like that. What we are claiming is this, whether it will interact or not, purely depends on the randomness over here. Okay? And as a result, these two quantities H p prime and H p double prime are going to be independent of each other. So, now this is our roadmap. Okay? We are going to prove that this H, which is the number of packets that interact with this path P, is at most 6n, okay, and with high probability. And then this is primarily what we are going to focus on. And then given that only 6n other packets interact with this path, we are going to prove that the overall time is going to be at most O of n, and this second statement is actually you can show it deterministically. Okay. So, the first, that is why we will spend more time on the first. All right. So, now, let us, in order to do this, let us get a few definitions down. So, now remember we are focusing on a path capital P, and E is some edge in that path, and so that is denoted by this position here, because that edge, each edge is fixing some bit. Okay, it is fixing some bit, and in this case it is fixing the jth bit. Okay. So, I am going to ask a question: which packets can reach V and have the possibility, I am sorry, can reach, sorry, it is U. Which packets can reach U and then have the possibility of traversing E. So, basically let us have a picture. E is going from U to V, U has this address over here, okay, and V has this address over here. Okay. They differ in the jth bit. So, which packets can reach U, go through V and move on. So, you need to be a little bit careful about the prefixes and suffixes. Well, let us be a bit careful here. So, which packets will reach U? It is not about their prefix, it is about their suffix, if you think about it, because the prefixes can somehow get a bit fixed and changed and reach U. But if it had reached U and then here the jth bit was fixed, okay, so then the prefix can be whatever, they can be fixed, but all the suffixes uj onwards should match that of vertex U. Do you see that? And its destination here, if you notice, if it had reached U, that means it had fixed to make sure that these were all matching this one, this part. Okay. And then after it traverses, so basically here, okay, so here you can actually mention this as U j bar or something like that. So basically here the destination should that particular bit should get fixed, and then after that particular bit gets fixed, then what it does after that we do not care. So, the suffix has to be, can be anything. Let's just yeah. So, basically this is Vj, yeah, you are right, yeah. We are assuming in this case if it is actually going through an edge, we are assuming that Uj is equal to Vj is equal to the complement of Uj. This is actually fixed.
Two packets that are reaching the same vertex,
Mm-hmm.
they need not be reaching at the same bit, right? Like they can be reaching at
They can be reaching, but if they have to go through that edge, they have to fix the exact same bit. If they have to, in this case, they have to fix the jth bit if they were to go through that edge. Okay, so let's proceed for now. So here, let's ask a few questions and try to answer them. How many packets? Now we know the structure of the packets that go through that edge. How many packets have starting address of the form don't cares followed by uj plus 1 and so on? That is of course 2 to the j minus 1. What is the probability of such a packet reaching U? Well, each of these bits should have been randomly chosen so that they fix their way to this particular node, right. So, that means each of them out of the two choices the correct choice should have been chosen. So, that is 1 over 2 raised to the j minus. Think of the number of packets along E. So, even if you think of the number of packets that reached that particular vertex u, it is at most 1 on x. Okay. So, let me maybe pause to make sure you get some time to think about it. Okay. So, let us go through the questions one by one. How many packets have the starting address of the form shown here, and why do we care about it? We are talking about those packets that can reach this node u, okay. And that is basically 2 raised to the j minus 1, because there are j minus 1 do not cares that we have, and all the rest, these are all fixed. If you look at the number of packets that can come to that particular node u, you cannot play with these values, but you can play with these values, and there are j minus 1 bits to play with. So, there are 2 raised to the j minus 1 options for that. Okay. So, that is the answer to the first question. So, now let us look at the second question. What is the probability of such a packet reaching? Okay. So, basically what does such a packet look like? It will have an address that looks like this. Basically, the first j minus 1 bits we do not care, it has some, it looks like something, and then the rest of them are fixed, right. What is the probability that such a packet will make its way to u? Well, in the bit fixing sequence, each one of them has to be fixed just right, so that the address matches u exactly, okay. Which means in the very first bit, the first star, whatever the star was, the random value associated with the destination should match the first bit in u. So, that happens with probability half. The second bit also should match with second bit of u, again probability half, and so on. Each bit has to be, the random bit has to be chosen appropriately, and that will happen with probability half, and there are j minus 1 such choices. So, this probability is 1 over 2 raised to the j minus. Oh, they have to, this is we are talking about reaching u, going through a particular edge and going through.
Why both of them have to be in jth position only? One can be j and one can be.
So, we are concerned about the number of packets that go through that particular edge E. This is our edge E that we are going to focus on. That is perfectly fine. Just this is perfectly fine, because this one just happened to be mostly matching u in terms of the bits that needed to be fixed, right. That is perfectly fine, but when it comes to u, what is needed is that if you look at this n bit string, and this is, let us say, the jth bit, all of them should not change anymore. Only then the focus will be on the jth bit, and that is important for us. Let us take this offline if you need a little bit more. Okay. So, now if you look at edge E, that is 1 out of some n, at most n number of edges in the path P. So, what is the expectation of the number of other packets that interact with that packet, that path P? That will be at most n, because you are adding that over all the edges. Okay. So, now we know we have this quantity h, we have established the expectation of h, at least an upper bound on that, and we need to ensure that we can apply Chernoff bounds. We know that the individual h p primes that add up to h, what are they? They are independent. So, we also know that, and we know that we are not making any claims about their probabilities at this point. So, their probabilities, each of the probabilities of h p prime equal to 1 or 0 are some quantities. We do not, they are different for each, but that only means that this h is the sum of random variables indicating Poisson trials, which is perfectly fine, because our Chernoff bounds are applicable here, okay. Which means that is it. The slide has only one inequality. probability that h greater than 6n is at most 2 raised to the minus 6n. This is the third inequality that I gave in the Chernoff bounds. Okay. And that is, see how low this is 1 over. So, and mu is at most n, and that is, so then it is at most 2 raised to the power minus 6. So, this is just 2 raised to the minus n.
Capital.
So, 2 power minus n is nothing but 1 over n, the whole raised to the power 6. Okay, so now let us see the second step in the analysis. So, what we have done is we have established that basically h is at most 6n with high probability. It exceeds 6n with very low probability. So, so now we are just going to assume that h is at most 6n. Okay. And how long will it take p to traverse this path capital P? Okay. And the answer is some 7n. And why? Because what is happening is a pipelining effect that is going on here. Okay. So, now let us look at this path P. Okay. So, it is from SP to RP, and the number of other packets that use any of these edges is at most 6n. Okay. And let us assume the worst case, that whenever this P reaches a particular vertex and it is in some queue. Okay, so there are some packets that have gone past it, but if there is any contention, it always gets the worst. I mean, remember you asked this question, right? How are contentions resolved? P gets to be the last guy in such contentions. When a bunch of packets reach a particular vertex at the same time, okay, there are already some packets in the queue, but when they get added to the queue at the end of the queue, P gets always unlucky. Okay, it is the last guy. But when you think about it, there is a nice pipelining effect that goes on here. So, let me see how you can explain this. So, let us say P is in this location at this point. There are a bunch of packets waiting in the queue over here. There are a bunch of packets waiting in the queue over here, a bunch of packets waiting in the queue over here, and so on. Okay. Consider this train, and let us say there is nothing waiting over here. Okay. This I call it a train, where there is P, and ahead of P there are all these packets in a series of vertices, and then at some point there is either an empty thing or it is touching RP, the destination. Okay. What can you say about the head of this train in each time step? The head of this train is this guy at the very beginning of this train. In each time step, that packet is going to move one step forward, or there are other. I mean, I am hand waving here, but or the train itself could get a little longer because some more packets joined and things like that. But if you look at it, the head, the position of the head will always keep moving forward. Okay. So if that is the case, if the head started at SP and it always kept moving forward, in n rounds, the head would have reached RP. Okay. After RP is reached by the head of the train, in every time step, what will happen? At least one packet from the head of the train is going to be knocked into RP, is going to reach RP. How many such packets can get into RP? At most 6n. And if that happens, at that point in time, P would be able to enter into RP. So, it takes n rounds at most for the head of the train to hit RP, and then 6n rounds for the entire train to fall into RP. Is that argument somewhat clear? Okay. And that establishes that in at most 7n rounds, your packet P is going to reach its destination. Okay. So, with that we will conclude. What we have done is we have analyzed the first phase of Valiant's routing. Some questions remain. So, for example, we have not talked about phase 2. So, the other question that we discussed a little while ago is, let us say a packet finishes its phase 1. Should it wait for all other packets to finish their phase 1? No, it can start its phase 2. And why is that? Again, that is something you need to convince yourself. Okay. So, I leave you with those two questions, and we will see some more examples in the next segment or so.